Hello, my name is Trevor Ablett, and I'll be presenting multimodal and force-matched imitation learning with a see-through visuotactile sensor. When humans manipulate an articulated object like a door or a drawer, their fingers use normal and shear forces, respond to dense tactile feedback, move quickly, can manipulate small, challenging knobs, and they don't require a firm, stable grasp. They can also use an approach based on pressing, pulling, and allowing roll and slip, compared to the more common robotic approach requiring a firm grasp and having a large arm motion. To get robots to do the same, we need dense tactile feedback, robust reaching of small targets, and complex control policies that can respond to this feedback. In this work, we use a see-through-your-skin visuotactile sensor for dense tactile feedback and reach refinement, and force-matched imitation learning for complex control policies that can leverage this dense feedback. An STS sensor has a small, inexpensive camera and deformable gel-based material on the surface, like a gel sight. The novelty of the STS is that the top layer is translucent and controllable lighting allows for multiple modes. Specifically, a visual mode, with the lights off, allowing one to view non-contact visual info, and a tactile mode, with the lights on, allowing one to view dense contact info as the skin and the painted-on dots deform. As part of our data collection process, we collect a raw demonstration via kinesthetic teaching. Throughout this demonstration, we use an STS sensor in tactile mode to measure unscaled force based on marker displacement. Next, we generate a new set of modified poses as input to our controller that will not only recreate the raw kinesthetic teaching poses, but the forces as well. Finally, we run a force-matched replay of the original trajectory, simultaneously acquiring an expert label for switching the STS sensor mode from visual to tactile at the point of contact. We do this n times, and we train our policy on these force-matched replays with behavior cloning, where our policy inputs are STS data, optionally an eye-in-hand wrist camera, and relative pose information, while our outputs are motion as well as STS mode. Our contributions for this work are a force matching method, a method using imitation learning to switch the STS mode, and a study of the value of STS data as a policy input compared with a wrist-mounted eye-in-hand camera. Here we show demonstrations and force-matched replays of each of our 4 tasks. We collected 20 demonstrations of each task and trained behavior cloning on the replayed data. Each task requires an initial reaching component between the handle or knob and the end effector, as shown on the right. Absolute pose is not provided in the observation. We also randomize the initial pose between the handle and the knob. These choices are meant to simulate the scenario, shown at the bottom right, where a mobile manipulator would pull up to a cabinet and not have reliable, repeatable, known base pose relative to the door. The initial reach requirement is meant to simulate the scenario that a simpler reaching or planning policy can get the end effector close to the object of interest. Here are our first tests of the trained autonomous policies. Our test results are on 3 seeds of 10 runs per variant per task, meaning that the average includes 120 runs. This video shows a single run of the autonomously running policy for each of our 4 tasks, including force matching, learn mode switching, and all 3 sensing modalities. The performance results on the right show that including force matching mode switching in the STS as input significantly improves performance. Here are a set of replay failures when the force matching is excluded. Notice that, because they are replays and not policies, the arm continues through the task trajectory even after it has failed. Here we show simultaneous STS data with mode switching, visual only, and tactile only for the glass knob closed task. During the reach, tactile only data is quite poor, whereas the opposite is clear during contact. Here are examples of failures with visual only and tactile only policies. The wrist camera is shown only as a reference and is excluded from these policies. Notice that the visual only policies effectively reach but often make poor initial contact or do not maintain contact. And conversely, the tactile only policies are often not able to reach at all, since without the wrist camera as input, they cannot reach the knob or handle effectively. In conclusion, force matching can be achieved with a low-cost visuotactile sensor or any other sensor that provides a signal proportional to force. STS mode switching can be learned via a simple expert labeling scheme, and force matching, mode switching, and STS's policy input each provide significant performance gains. Thank you.